Hello students, in previous lecture I have taken some examples on equivalence relations and I told you that in this session I am going to talk about the one more type of relation which is known as antisymmetric relation. Antisymmetric relation. So what is meant by antisymmetric? Relation. A relation R on X, non-empty set X, is antisymmetric. Antisymmetric if xy and yx belongs to R, implies x must be equal to y for any xy belongs to x. For any two pairs, if xy and reverse pair yx is there, then x must be equal to y. X must be equal to y. For example, on set of real number, if I take two real numbers are related if a and b are a less equal b. For this relation, if a is less equal b, b less equal a, then a must be equal to b. A must be equal to b. So if a, b and b are there, then a must be equal to b. So that type of relation is known as antisymmetric relation. Antisymmetric relation. And then depending on this antisymmetric, there is concept of partial order relation. Partial order relation. A relation I'll denote it by less equal symbol defined on X, which is non-empty set, is partial order relation. Partial order relation if it is reflexive, symmetric and antisymmetric. Antisymmetric and transitive. Depending on this partial order relation, there is one more course which is known as lattice theory is developed only on partial order relation. So what is the difference between equivalence relation? Okay. So what is the equivalence relation? A relation tilde defined on X is a equivalence relation if it is reflexive, symmetric and transitive. So there is only difference between antisymmetric and symmetric. Antisymmetric and symmetric. So we have taken few examples of equivalence relation. I also explained the equivalence classes theorem that every equivalence relation on non-empty set X defines its partition and conversely every partition defines equivalence relation. In previous lecture I have taken two examples of equivalence relation defined on Z. For set of integers is countable set. So you can define countable number of partitions defined on Z, and that's why there exist countable number of equivalence relation on it. So among them only we have studied 3-4 relations on it. If you go through books, you will get other type of examples which are equivalence relation defined on it. So here now we have to distinguish these two relations, partial order relation, equivalence relation. Here I am using less equal symbol for partial order relation. We know that on number system, set of real number if I take and less equal relation if I take. For AB belongs to R, A is less equal B if A is less equal B. Then first A is less equal A for every A belongs to R. Second, for AB belongs to R, if A less equal B, this is the usual less equal relation. A less equal B, B less equal A, this must implies A equal to B. So, it is nothing but antisymmetric relation. Third, for ABC belongs to R, A less equal B, B less equal A, C, this must implies A is less equal C. Therefore, it is reflexive, antisymmetric and transitive. So, usual less equal relation on set of numbers is reflexive, antisymmetric, transitive, therefore it is partial order relation. Note, this relation is antisymmetric, which is not symmetric. For this, if I take the pair 2, 3, for 2 and 3 belongs to R, 2 is less equal 3, but 3 is not less than 2, 3 is not less equal to, means 2, 3 lies in this relation, but 3, 2 is not there, therefore it is not symmetric relation and hence it must not be equivalence relation on it. Then in your mind you will say that if a relation is symmetric, then it must not be antisymmetric, or if it is antisymmetric, then it must not be symmetric. But this is false. So think about the example of relation which is symmetric as well as antisymmetric relation on non-empty set X. Okay. So this is example. Okay. So this implies less equal relation, usual less equal relation, less equal, defined on or any number system, it may be set of natural numbers, integers, rational number, irrational numbers, or any non-empty set of numbers. Okay, is partial order relation. Is it clear? But not equivalence relation. I am not interested to study concept of partial order relation in detail. We are also studying this equivalence relation for the purpose of studying congruence relation on set of integer. That is the main aim of equivalence relation in this level. Okay, we are not interested to study that in detail. So in our syllabus, so many examples are introduced, but that examples are only for your practice. Our aim is to study what is the congruence relation defined on Z and how it is equivalence relation. That is the main aim for studying the equivalence relation. But as partial order relation is also mentioned in your syllabus, antisymmetric relation is explained. That's why I am explaining this. Is it clear? So now, so this is this one. Give example of relation on non-empty set X not equal to phi, which is symmetric and antisymmetric. It is symmetric as well as antisymmetric. It must be symmetric as well as antisymmetric. Okay. So solution. Let X be non-empty set. Then phi is symmetric first and antisymmetric. Check. Second, if I take XX pair, where X belongs to X or X belongs to Y and Y is subset of X. x belongs to y, y subset of x. Then Ry. Then Ry is symmetric and antisymmetric. Symmetric and antisymmetric. Third, if I take Rx like this, set of order pairs xx where x belongs to x is equivalence relation and partial order relation on x. This is unique. This is unique. I can give so many examples of relation which are symmetric, antisymmetric for any subset y of x. It is possible. Even empty set is symmetric and antisymmetric. So, if I take only xx pair, which is I can call it as equality relation, say, in which first and second components are equal, then we will say that it is equality relation. So it is symmetric, antisymmetric. But for equivalence relation, I want it to be reflexive relation, and due to the reflexivity, all xx pair must be there. In some books, this is denoted by del symbol also, which is called a diagonal, of x cross x set. Okay, so this is known as diagonal of x cross x. So diagonal of x cross x is always equivalence relation as well as partial order relation. Okay. Now set relation then symmetric, reflexive, symmetric, transitive, antisymmetric, equivalence relation and partial order relation. N. Set of natural number, if I take this one. So AB belongs to n cross m such that A is less equal to B. A less equal to B. Then if I take on this, it is it reflexive? Yes. Every element is less equal that. Is it symmetric? No. Is it transitive? Yes. It is antisymmetric? Yes. This is not equivalence relation, it is partial order relation. If I take again n set of AB such that AB belongs to n cross n such that A divides B. Every natural number divides itself. Symmetry. Okay. So here 2, 3 belongs to 2, 3. So this is the R, but 3, 2 doesn't belong to R. 3, 2 doesn't belong to R. Again here, say 2, 4 belongs to R, 4, 2 doesn't belong to R. So it is not that one. Transitive, if A divides B, B divides that hold. If A dividing B, B dividing A, antisymmetric, no, partial order relation. If I take again say Z set of AB belongs to Z cross Z such that A divides B. A divides B. Is it reflexive? No. Okay. 0 doesn't divide 0. Is it symmetric? Symmetric? 2, 4. No. Same reasoning. Is it transitive? Yes. Is it antisymmetric? No. 2 divides minus 2. Minus 2 divides 2, but 2 not equal minus 2. So it is neither equivalence nor that. If I take now, say Z star is equal to Z minus 0, then AB belongs to Z cross Z such that A divides B. A divides B. Then it is reflexive, 0 is not there. Symmetric, no. Same reasoning again. Antisymmetric, no. Transitive, yes. Not equivalence, not equivalence. If I take now power set of n, set of all subsets of n, set of all subsets of n. So it contains set order pair AB such that A is subset of B. A and B are subsets of n, then A is related to B if A is subset of B. Every set is subset of itself. If A is subset of B, then B may not be subset of this. No. Transitivity, hold. A subset of B, B subset of C implies A subset of C. Antisymmetric, yes. If A subset of B, B subset of A, hold. Not this hold. Is it clear? So in this way, you can construct lot of examples of relation defined on n just, which is neither reflexive, it is symmetric, transitive, antisymmetric, etc. Like that. Okay. So with the discussion, I like to stop equivalence relation, equivalence classes concept here. Now in next section, we'll study concept of functions. Function is also one type of relation which you are studying function from 11th standard. So thanks for listening my sessions carefully with your patience. Bye bye.